My name is Michael Aeberhard. I've been with the research department for about 6 years now in Munich with BMW. Started with my PhD thesis there, kind of still working on finishing that up. Hopefully it'll happen in the next year or so. I'm sure a lot of you know about this problem. But I started there with working on automated driving, more in the perception area. Nowadays I do more in the planning area. I'm here with a colleague of mine, Julian Thomas. He's the other colleague who's in bold. And some of the other colleagues here that we've listed have also done a lot of contribution in our department with getting ROS up and running and really working on the infrastructure. So I'm going to talk a bit about today what we've done over about the last year and a half, 2 years with ROS, and show you some of the experiences we've done with this. But just a quick overview of history of automated driving at BMW. It's not new. It's coming up on about 10 years of automated driving at BMW. We've been doing this for quite a while. And we started with a BMW track trainer. It was a car that drives autonomous on racetracks, so automated driving BMW style, I guess you could say. And then after that, we slowly got into other functionalities. First, the emergency stop assistant. So in case the driver has a heart attack, the car would do an automated maneuver to come to a stop on the right side of the road. And then in 2011, we had our first successful demo of an automated driving function on the highway in rural traffic. And that's a system we've been continuing developing over the last few years. But some other projects have also happened in the last years, like automated driving at the vehicle's limit, where we were able to bring a car into a drift state, keep it in a drift around a corner, and then bring it back out of drift, just to prove that the control algorithms can be so good to control a car at and beyond the limits of what's possible with vehicle dynamics. So that was quite a success. We also actually showed that 2 years ago at the CES in Las Vegas. We were at CES again this year, where we had two functions, fully automated remote valet parking, so you actually physically get out of the car and then the car parks itself in its parking spot. So this was our first function without a physical person inside the car in automated driving. The other function was 360-degree collision avoidance. So this is a car at low speeds which you cannot crash. So we challenge people to get in the car and drive against walls and obstacles and try to cut corners to try to crash the car, and it just wouldn't. It would stop just before hitting a wall. So we proved that that's also possible. And for more information, we actually published a paper at IEEE Intelligent Transportation Systems magazine this year, where there's a lot more technical details, mostly about the highway project, but also about our algorithms with grids and everything. So if you're interested in the algorithms and want a good place to start to learn about how we're doing this stuff, it's a good paper. And we haven't really communicated this yet, but these two projects were already running ROS in the background. So at CES this year, if you saw these two BMWs, they were using ROS in the background. We didn't use Arvis to visualize it or anything like that. It was just running in the background to do the environment detection. So our whole grid algorithms were running in ROS, and the planning algorithms for the parking function were also running in ROS. We're also involved at the European Union level in a research initiative for automated driving called Adaptive. There are several companies in the consortium, OEMs, suppliers, universities, institutes, and they were working on automated driving at the parking, city, and highway level, also looking at the illegal aspects. It's kind of trying to get all these people together to figure out how to bring automated driving one day to market. And BMW will be doing a prototype, which will be running ROS in this project, for conditional automation on the highway, so driver out of the loop, and partial automation in cities, so driver still in the loop. So just for people who aren't quite familiar with what the architecture looks like, well, I guess you guys are familiar. I'm talking to a robotic community. It's basically the same thing. You know, the car is a robot. You have sensors as input. And we have what we call environment models. So we combine all the sensor data and bring it to a level of abstraction which is sensor independent to kind of get a description of the whole environment. And then based on this environment description, which may also contain situation interpretation modules, the ADAS functions, ACC and automated driving and everything else that you have in a car for ADAS, also ADAS is Advanced Driver Assistance Systems. You do the planning, trajectory planning, state machine types of things which are specific for a single function. And then you have some sort of output which either goes to the HMI, so the driver knows what's going on with the car, and then of course to the vehicle control systems that actually then control the car. So that's the basic architecture. Our new research prototype that we're doing for adaptive projects is going to be a 3 Series, a 335 GT. So we got a nice motor in the front of that car, and which makes it fun to test with. At the time when we decided to build this car, this was the best car with the best advanced driver assistance systems package, which we had. So we chose this car, and then to build on top of what's already in the car in series production, add additional stuff into it, and make that our new research platform. I call this a Generation 2 because our old cars were 5 Series, 2010 year 5 Series. So now we're with this 3 Series. To look at the basic sensor setup, what do we have in the car? One of the main sensors is a laser scanner, all around the car, front, rear, and 2 on the left and the right. Long-range radar, it's the same one that we use in series for the active cruise control function. Camera is also a similar sensor used for the lane departure warning in series, but of course we're using it for more than just that. Then we have 2 more long-range radars in the back to extend our field of view to the rear, and then 4 short-range radars which are around the vehicle. So basically, if you were to remove the laser scanners in this sensor setup and the long-range radars in the back, that's basically the sensor setup of the new BMW 7 Series. So we're actually, our research prototype isn't that far away from what's already on the hardware inside a series production car. So this is what our architecture in the research department looks like. This is the stuff we put into the car that's not series production. So we access all of the data in the car over CAN, Ethernet, FlexRay, over gateways. So we have these gateway components in the car that then convert everything CAN, Ethernet, FlexRay to a single generic Ethernet interface. That all runs over a switch with a lot of virtual LAN networks. And then we access the data over the several computers that make up the components over the switch. And one of those components is the environment and function computer running Linux and ROS. And the other computers are a display HMI computer running Windows. And then we have our real-time system from DSpace Autobox 2, which then does the real-time software. And then basically, out of the motion control computer, you get the signals which tell the actuators what to do. Then there's another layer of safety to make sure it doesn't do any errors. And then it goes to the actuators and for the gas brake and steering. And we also have a time server which tries to synchronize all of the different computers in the car. So, why did we go to ROS? So, in the past, we had this thing called microframework. It was our internally developed framework, which we used to do ADAS prototyping in our research department. It used a shared memory concept, so it shared pointers between software modules. It was all one process, and has a really nice synchronized execution of software, so it's not asynchronous like ROS is. But this is what it looked like if when the automated driving function was on. So you have here at the left your states. So now we see detect a slower car. The car is doing a lane change. You see our digital map. On the right here a bit some situation interpretation. The blue boxes are object hypothesis. And this is what we worked with for quite a long time. So here we see an overtaking. So, but in the automobile industry, especially in Germany, years ago, there was a decision that all of the car companies kind of had their own frameworks, and there was a decision, you know, hey, let's share the resources and make one framework, and then a commercial product actually does exist in the automobile industry for doing framework type work. It's called ADTF, and it's very tuned towards the requirements of the automobile industry, which is really great because there are a lot of requirements, especially when you go closer and closer to series production, and ADTF is a perfect solution for this. So we were at the point where we wanted to say, okay, our internal framework called microframework, it's starting to reach its limits. Either do we keep developing it, or should we, you know, join our pre-series colleagues and go to ADTF? That would have been the obvious choice, actually. But then there was this thing called ROS, and some of our colleagues in the US in our Mountain View Tech office, they were starting to experiment a few years ago with ROS. Our car IT colleagues in Munich also started to experiment a bit with ROS, tinker around with it. They made us aware that this exists in the robotics community and that it's being used by a lot of research institutes quite successfully. So then we started to try it out in Munich as well, just to kind of see what it can do. We were actually quite happy with what it can do, especially because it's open source. So like if something isn't the way you want it to be, you can change it, which is a big advantage, especially for the research department, since we might want to do something that another framework cannot do yet. And it has a distributed architecture, so that was really interesting that you could have it run over several computers with different processes, and if one node crashes, it doesn't crash the whole system, so that was a really nice feature. And a huge selection of this off-the-shelf software, so if you just want to try something out real quick, like G-mapping or something, then you just publish the correct messages and you can see what you can do very quickly. So obviously, I guess the choice we made is obvious, or else I wouldn't be here. We ended up going with the research department with ROS, but why? We wanted to, autonomous driving basically is robotics, so we wanted to get a better connection to the robotics community, which is widely using ROS, and it has a very, very large user base. And large user base means stability and reliability because somebody else probably already solved the problem you're having. And that has been the case for us when we always had a problem. Answers.ros.org, do a quick search, and somebody's probably already solved it. So that's also really cool. And like I said, you can do quick testing of already available algorithms and software from what's available, open source. And one thing we do in the research department often is cooperate with universities or other research institutes. And ROS is just a great platform to where everybody knows how to work with it. There's the ROS messages, and then it's much easier to work, to cooperate with other institutes at a very practical level, which was in the past a bit more difficult. And also, since we're the research department, we should be trying something new. You know, this it's a risk, I guess, going with ROS instead of going with the commercial product. But we wanted to gain experience. How does it work? Is it something that has more potential or doesn't? And so we wanted to simply gain this experience using ROS for BMW, and then see what happens. Which we're still doing. See what happens. So basically our ROS architecture looks like this. It's very, very simplified version, but like I said, we get all the Ethernet data in, and then we have a ROS node that basically does Ethernet to ROS. And these yellow interfaces are our own custom-defined ROS messages, which basically define what our input-output interfaces are to the ROS system. And then we run our algorithms, environment perception, sensor fusion, situation interpretation, planning, etc. And then output is basically a trajectory and some HMI triggers. And then we have a ROS to Ethernet again, which then puts the data back to the gateways or directly to the real-time computer, where it then gets processed in real time in order to drive the trajectory. We can do this in the simulation. So basically, when we're connected to our BMW simulator software, we have a node that does simulator to ROS. So we basically publish the correct messages that are of interest to us from the simulator's API, and then we're able to develop our algorithms as if we were in the car. Then we also have a ROS to simulator to drive the vehicle in the simulation. And if we go into the real car, all you do is have to change the ends. So instead, you have gateway to ROS or hardware to ROS to publish the same ROS messages. And then the nodes that you're running that actually do your algorithms and your intelligence and everything, those are exactly the same in the simulation or in the car. So this is a really cool advantage of setting it up this way. Then at the end we have a ROS to Autobox, which then pipes the data over to the DSpace micro Autobox, which, like I said, then does the control algorithms in real time. Also this year, which was really cool, the MathWorks released a robotic systems toolbox, which natively does a lot of interesting ROS functions. We've been using it mainly to analyze and read ROS specs at the moment, which is very useful to kind of evaluate your system, to analyze what's going on, and to find errors. And a lot of our old software that we have, so we used to be very heavy users of the DSpace Autobox, especially for real-time stuff. But we also had a lot of stuff that doesn't necessarily have to run in real time, also on the DSpace hardware. And with the integration of Simulink and ROS, it's very easy to bring this software out of this real-time system and let it run in the ROS environment. So now to the visual part of my presentation. Take a look at what some of our cars look like in the visualization. So this right here is our i3, the one we had at the CES this year. We just took it onto a drive around in the city to kind of visualize some laser scanner data. You also see the odometry path here in the back and the vehicle dynamics on the side. You don't see it really that well on the left. But we're not driving automated here, it's just manual driving, just to kind of get an idea of what the laser scanner data looks like. And all of that, we don't use a big laser scanner on the roof. We wanted to avoid that, so all of our sensors are really nicely integrated in the car that you can barely tell that there's anything in it at all. So that was it's very important for us to work with sensor configuration in this manner. So here's the same scenario with our occupancy grid algorithms. Green is free, red is a static obstacle. Like I said, the same scenario. You can also see there's some dynamic objects usually around the car, but we do a good job of filtering them out so that the grids are truly a static environment representation without any artifacts from dynamic objects. And this is very important at high speeds because you want to do your planning against the static environment, and the dynamic environment, you use a different algorithm in your planning to do collision checking there. So I actually took some of these videos this week on our test tracks. I did a lot of development there. Took the opportunity to do some visualization. So here's a laser scanner on our lane marking detection and the object detection. What's coming from the sensors on a basic highway simulated track. You can see the images a bit on the left. So now we're going here into a curve. Still driving manual at this point. Just kind of get an idea of what our algorithms in the environment model area look like, the interfaces at least. Now, of course, for automated driving, you need to localize yourself on a highly digital map. So this is what our map looks like in the background. It's grid-based, so we have landmark data and grid data in the map, which you all convert to a generic grid representation. Then you see the heat map, that's our localization hypothesis, where we are. And you can see that we're getting quite an accurate localization. We're not using differential GPS, we're using just a normal GPS that's built into the series production car. And we're able to get very, very accurate localization with these maps. And all of this that I'm showing you now is running on one PC. Since we're the research department, we just buy the top of the line i7 and then get started, so we don't really have any restrictions like our colleagues do in the pre-series departments. Use the most powerful computer we can get and then have fun. So now you see the more logical layer of the map, so you actually have the geometry of the roads, you have identification of what type of lane it is, so the yellow is the emergency lane on the right side, now going into another curve, and as you can see the localization does a good job of keeping the car localized properly, even though the lane marking detection sometimes doesn't match up perfectly with what the map is saying. That's not a big deal because there's enough redundancy in the background with other sensors in order to keep the localization quite accurate throughout the whole runtime of the system. Now, of course, we have objects, we have maps, we know where the road is going. Now we need to plan something, and this is our trajectory planning, what it looks like in the visualization. You can now see that the road we want to be driving on is green, which means that the maneuver planning has chosen to drive on that lane. And then the trajectory you see in front of the car, the darker green or lighter green, I guess, is now the reactive trajectory planning that's being done, which actually gets sent over to our real-time computer, which is then actually driven. There's actually 3 layers of planning. So you have maneuver planning, then you have a selection of the lane, and then a short-term reactive planning. Now, finally, turning the system on. What happens when the car is really driving automated? So you see at the lower right, it's off. Now we turned it on. Car's in lane keeping mode. It's detected that there's a car in front. My colleague can see the yellow line is now pushing his speed up. We've detected that we're slower, the car does a lane change to overtake the slower car in front, since we would like to be driving faster. And all the decision making for the lane change is completely automated, so the driver really isn't doing anything here. In Germany, you should always drive on the as far right as possible, so the car will go back to the right lane, does an automated lane change, and will just get you to your destination in this manner. So what are some of the other stuff we did? So we had the need to develop some other things that the ROS tools out of the box didn't really fit for us. We did a lot of RQT plugins, especially for RQT plugins that simulate input. Like if I wanted to simulate that the driver presses a button on the steering wheel, I can do this over a GUI. So we made a little GUI that publishes the correct topic in order to simulate a lot of stuff, which really helps in development when you don't want to, when you want to basically get rid of the hardware as a potential error source. Do some simulation. We've also wrote some other GUIs for example, here's one that wraps or does our own implementation of bag record and play. We actually want to record do a ROS param dump and load with the bag that we've recorded, some metadata, like we want to know who's driving, what type of situations there are, so there's some extra stuff that we want to save along with bags, so we kind of wrap this in one tool. Another little nice feature, you know, it has this a 2D map, so when you're playing back a bag, you can kind of see where you are from an OSM map, but maybe, I guess, that won't be necessary when MapViz is working, we'll just use that instead. And what else you saw, we tend to not, in RViz, we tend to not use markers to avoid traffic. So we created a lot of plugins that work on our specific interfaces, so we can access directly the Ogre API and do some really neat things, which the markers may not be able to do. For debugging, like let's say I wanted to know some internal value or some internal state of an algorithm, then I might, for quick debugging, do a marker to kind of see what's going on. But in general, we try to make really nice plugins that also look good, that are nice to present, because of course we want to also present this stuff at some point, that work directly on our interfaces. So that's usually what we do. We also like the selection mechanism, so you can actually, so if you develop the plugin correctly, you can click on an object and then decide what you want to display from the message in the selection window. So we use that a lot for also debugging to kind of not just see where the object is, but you click on it and then you get a lot of the internal attributes directly in RViz. So that's a really cool, almost out-of-the-box feature when you're doing a plugin. So what do we like about ROS? Reliability and stability. Like at the CES this year when we had it for our parking demo, it ran from morning to night without any problems at all. It was really great. It surprised us how well it worked, even in the Las Vegas heat. Everything worked out really good, so we were quite happy with the performance there. The minimalism of what our basic ROS node is also really cool. It's not much code to actually start using the ROS infrastructure, so you can have really lean nodes. And distributed architecture, like I mentioned, is also really great. So if one node crashes, you might have a backup node which might take over those duties, and it's all distributed. So you have increased reliability as well. And the ROS message concept is cool because anybody can understand the ROS message. You can really discuss very easily about the interface, and you can discuss at a level that's very close to implementation. So a ROS message can be directly implemented using C++ or Python, and so you're talking about something very real using a ROS message instead of doing Excel sheet for you to say what are the values that the interface has. So that's very useful. All of the off-the-shelf tools are really cool to help working with the data. RViz, RQT, back diagnostics, all really, really cool stuff. And when we also decided to make the change to ROS, you could tell that there was future potential in ROS, and we wanted to try it out just to make sure that you know, somebody at BMW is getting involved with ROS to make sure that we're ready once it maybe does become something more. And ROS 2 and ROS Industrial, they are going in a really good direction, I think, where the potential could be pretty big. And of course, there's lots of software packages to try out, so if we want to try something out new and we haven't developed anything on it yet, there probably is somebody in the robotics world that has done something kind of similar, and a quick search on the internet might lead to a ROS package that we could try out real quick to see if this idea we have for an application makes sense. So what are some of the things that we think could be improved? I guess it's just some ideas. Maybe some other people have also had these problems. Be interesting to know. So I think more options in transport mechanism would be cool. But I think DDS and ROS2 will solve this. So I don't think this is an issue at all anymore. But we also do a lot of work on the GPU. So what's costing us a lot of performance is when I want to communicate what's in GPU memory from one node to another. So I have to take it then to the CPU, transport it to the other node, and then push it back to the CPU to the GPU. It'd be better just to have a shared memory GPU transport in order to avoid all that and really increase performance. So that'd be something interesting. And what we also tend to do, we tend to update the comments of our ROS messages quite often. In order to tell people, use this like this, and if it was confusing, we need to update it so people understand better. But unfortunately, every time when you change a comment in a ROS message, your old bags don't work anymore, and you have to do the conversion and so on. So it'd be cooler if the ROS messages didn't work on the whole ROS message as an MD5 checksum, maybe just on the actual data and the variable names, and just ignore the comments. Maybe be a bit better for the compatibility when you're doing a lot of changes, especially in early ROS messages. And I think the tools can always be improved. ROS Architecture, I guess there's a list of stuff that could be done. What we had in our old framework was a labeling framework. So, of course, to evaluate data, to get your true positive, false positive rate kind of stuff, you need to do some kind of manual labeling, have some kind of tools where you can label objects, tell them what type they are, to do your evaluation. So that's one thing we might be looking into, is kind of trying to do like this labeling framework in order to generate ground truth data for evaluation purposes. Some kind of GUI to do node management would be cool. Node manager from FKI that's in that direction. We haven't really, some of our colleagues have tinkered around with it. I'll have to take a closer look at it as well to see if that's already maybe the solution. And right now we're like a crazy hodgepodge of launch files, since we have several cars now running ROS, and all the cars have slightly different configurations, and you have to combine the launch files correctly. It'd be interesting to see if there's a better method of having a better inter-robotic configuration system. Maybe it's possible, maybe not. But one of the big things which probably will make it difficult for ROS to kind of get closer to our product, at least in the automobile industry, is this compliance to industry standards, to verification processes. ISO AutoSAR, for example, is a software specification for how software should be developed in the automobile industry, and at some point, the closer you get to actual software that goes into series production, you need to start becoming compliant to all of these standards in order to make this software usable in a real product. So it'd be interesting to hear if there are also other companies, especially car companies, using ROS, and if this is also a concern, or if ROS, there are any plans with ROS Industrial, for example, they're maybe doing something in that direction, but in a different industry. But maybe what they're doing, it could be something that we could learn from as well. But that's actually it for my presentation. Ever any questions, feel free to contact me. I hope you've enjoyed learning about how we're using ROS, and we've enjoyed using it, so I'd like to take this opportunity again to say thank you to everyone who's contributed, who's done a lot of interesting packages that we're using, and yeah, thank you.